Good morning. Welcome to my favorite students. Okay. Let's just look at where things are. We've had a long weekend. Maybe it's hard to get back in the mindset of school after that. Okay, on Tuesday, your first assignment is due from Chapter 7. Of course, in Chapter 7, we're talking about the energy equation and so on. And then a week from today, we're having our bonus quiz. And as I mentioned previously, our bonus quiz, it can't hurt you. It can only help you. And it's going to be sort of on the old material. Now, I'm not going to ask some minutia question, like I'm not going to ask the smallest piece of trivia that I can think of. It will be some of the main ideas behind the earlier material. So then Tuesday the 17th is, our last assignment is due on Tuesday the 17th, and that's actually our last class day. And then for this class, we have our exam on Thursday the 19th. And so if you think about it, we're getting close to the end of the semester, really. So any questions related to the end, to the announcements? Okay. Well, we're continuing our discussion of the energy equation today. And just to refresh our memory of what we were talking about last time, let's look at the energy equation formula and talk through each of the terms and how this is an improvement on what we've been doing before. You'll remember that in the earlier lecture what we did was we did sort of a side-by-side comparison of Bernoulli's equation with the energy equation because they do look similar. There are many of the same terms, but in the Bernoulli's equation we were limited by its accuracy is only as good as how closely we follow four assumptions. The four assumptions being for an inviscid fluid, meaning that it has no viscosity, which is incompressible, which is for steady flow, and applied along a streamline. So those were the four assumptions that we had to use with Bernoulli's equation. And then in Bernoulli's equation we had a pressure head term, a velocity head term, and an elevation term. And many of those are here, but with a few exceptions and adjustments. So the pressure head term is the same. In the velocity head term, if we're looking strictly speaking at the full-fledged energy equation, then we can use a kinetic energy correction factor, which adjusts for the fact that here in the energy equation you'll notice that there's a bar over the velocity. So it's the average velocity squared. Whereas when we were using Bernoulli's equation, it was the velocity at a single point, and so that we didn't have to worry about the fast velocity at the center of the pipe compared to the slow velocity at the edge of a pipe. So that's the interpretation of both the bar over the V and the alpha. Z is just the elevation term. H sub P is one of the new terms, and it's talking about a pump. And you'll notice that the pump head term is only on one side of the equation. And what I've told you previously is that it's very important that we select location 1 and location 2 according to the criteria that water flows in the direction from 1 towards 2. So whether we apply the energy equation for an open channel, like a river, or if we're applying it in a pipe, which is closed conduit flow, water goes from 1 towards 2. And so we sometimes call the location that the water is coming from upstream, and the direction that the water is going to downstream. Okay. And so what you'll notice is that the pump head term is on the left side of the equation. And so what that means is if you've got water going from 1 towards 2 and you've got a pump in between, you don't always have a pump, but if you do have a pump in between, what it's going to do is it's going to add energy, and so that this equation says that all of the energy at 1 is equal to all of the energy at 2 plus how much is lost. And so all of the energy at 1 plus the amount that was added at the pump is equal to the energy at 2 plus what was lost. So what side of the equation, the pump head term and then later on the turbine term and the losses, both of those terms are on the right-hand side of the equation, meaning that that energy is removed from the system as water flows from 1 towards 2. So any questions about the energy equation in general before we apply it to this example? All right. So here we have a series of tanks. We've got the west tank and the east tank. And water is flowing from the west tank to the east tank. Now, in the previous example, when we were working with two tanks, what we did was we selected location 1 at the water surface elevation of the left tank, because water was flowing from the uphill towards the downhill. And then 2 was the water surface elevation of the downhill tank. But here, if you read the problem statement, it doesn't say anything about the water surface elevations. So we don't know where is the water levels. But what we do know, you can sort of see that I've indicated some dimensions here. We know that the pipe is sloped at 3%. That means that if we go 100 meters of length, then the elevation drop would be 3 meters. So that's the percentage. That's how to interpret the percentages for whatever distance horizontally, what the vertical component of that drop is. All right. So we have pressure gauges at this location and that location. Water is flowing from the west to the east tank, and there's a pressure drop of 86 kilopascals. And so we have a pressure meter. Now, if the water wasn't flowing, let's just say it was the hydrostatic equation. Would you expect the, let's call this location 1 the first tap, and location 2 is the downstream tap. So if it was just static conditions, the water's not flowing, what would you expect the pressure difference to be, 1 versus 2? And I'm not saying a specific number, but like higher versus lower. What would be your guess? From the drawing, you can see one of them is at a higher elevation and one is a lower elevation. So what's that going to do to the pressures? Somebody has to guess. That's the rule. What do you think? Where's the pressure going to be higher? If it's static condition. If the water's not flowing, here is 1, right there. Here is 2. So where would the pressure be higher? At 1 or 2? Why do you think it's at 2? You're right. Right, of course, right. Hydrostatic equation says delta P is delta H times gamma. So location 2 is lower than location 1. So if the water wasn't flowing, then the pressure would be higher at location 1. But what this is saying, I'm sorry, the pressure would be higher at location 2. All right. What this is saying is that actually the pressure is lower. It's saying P1 minus P2 is 86 kilopascals. And so that means that the pressure at 1 is higher, and in the case of water is flowing. So why? If the hydrostatic equation says that the pressure at 2 should be greater, then why is it that when the water is flowing, the pressure is less? Any guesses about that? Due to head loss. That's right. It's because of the pipe friction. As the water is flowing through the pipe, that resistance that the pipe is imparting to the flowing fluid, it steals pressure. You know, when you lose energy, the energy can be lost in 3 places. You can lose energy as velocity, you can lose energy as elevation, or you can lose energy as pressure. And in a pipe that has the same diameter, the velocity has to be the same, because the continuity equation says that whatever flows into the pipe has to flow out of the pipe. So V1 equals V2. And so the elevation is changing, but it's changing not because of energy loss. The elevation is changing because of the pipe slope. So what I'd like you to do is calculate the head loss. Calculate H sub L based on location 1 being right here, this point that's closer to the western tank, and location 2 being right here, closer to the eastern tank. I'm going to pause the recording, calculate H sub L, and it's going to have units of meters. All right. So again, what we're trying to do is we know that as the water flows from the first location to the second, we can assume that the pipe diameter is constant because it's not saying anything about the velocity changing. It's not telling us that there's a difference in pipe diameter. And so the safe assumption is that, and it looks visually from the thickness of the line, that the pipe diameter is the same the entire journey from 1 to 2. So what that enables you to do is say that V1 equals V2. So we're going to cancel out the velocity head terms. We're not told anything about whether the flow conditions are laminar or whether we should use some specialized kinetic energy correction factor. And so if we did have the velocities, then we could still just assume that alpha is equal to 1. But since the velocities are the same, then the kinetic energy correction factor is neglected. So let's look at the solution here. We have a pipe length and a slope, and the measured pressure differential is 86 kilopascals between the 2 points. And so we need to have a Z1 and a Z2 to go into the equation. So we can just assume any value for Z2, and then as long as Z1 is relative to that same datum, then we'll get the correct answer. So I said, let's say Z2 is 0, and we get the elevation Z1 by multiplying the physical slope by the pipe length. There's no pump, no turbine, so a lot of these terms cancel out. The velocity head term, the pump head term, the other velocity, Z2, turbine term. So to rearrange it in terms of head loss, we get it's 25.12 meters of head loss. All right, so any questions about that example? All right. Well, let's talk about power. We discussed it briefly in the last class, and you remember that power has units of watts. And if we have a flow rate in terms of cubic meters per second, the unit weight of the fluid in terms of newtons per cubic meter, and then the turbine head. Now H sub T is talking about how much energy is removed by the turbine. And the way that you would know how much energy is removed by the turbine would be by measuring the pressure, both upstream and then downstream of the turbine. What we're going to do is we're going to apply the energy equation to find H sub T, and then you're going to substitute the H sub T that you find from the energy equation into the power equation. So this is going to be a two-step example. For part A, we're assuming that there's 100% efficiency in converting potential energy into electrical energy. But then in part B, I'd like you to consider what if that exchange was only 70% efficient? What if there are some losses? And the losses, when you're having hydropower like this, it might be mechanical losses like the vibration of the pump. And so any energy that is exchanged into vibration or heat is a really big one, isn't going to be turned into electricity. And so in part B, consider what if it was 70% efficient? Then would your power be higher if there are losses, or would it be lower if there are losses? And so I don't want to specifically tell you what to do with that 70% factor, but I think once you calculate the amount of power at 100% efficiency, it'll be pretty obvious what you need to do if it's 70% efficient. So just to summarize, here we have information at location 1, which is the upper reservoir. Here we have the water surface elevation at the upper reservoir. And let me ask you this. What is the pressure of the water at the top of that reservoir? Exactly, it's 0. It's atmospheric pressure. And we'll work this problem in terms of gauge, just because here the atmospheric pressure at the upper elevation of the reservoir is the same as at the bottom. So location 2 will be this lower reservoir after the water has exited the turbine. And the reason why we choose that as location 2 is we have the elevation of the water at the lower reservoir. The head losses are defined for us already directly. Now, in a previous example, we had to calculate the head losses based on the length of the pipe, the velocity of the flow, a roughness factor, and so on. But here that work's already been done for us because this example is more about the power efficiency than it is about calculating the head loss. We have the diameter of what's called the penstock, and the penstock that's just a specialized name for the pipe that takes water to the turbine from a reservoir. And we also have the flow velocity, 2.4 meters per second. And so you're going to need those dimensions, the diameter and the velocity, in order to calculate the flow rate. All right. So again, this is a two-step process. Step one, use the energy equation to calculate H sub t. And then step two, calculate the power generation using here the power equation. Okay. So here's my sketch and the energy equation. So in the problem statement, we are already told the elevation of 1 and 2. And so we're given Z1 and Z2. Location 1 and location 2 both have atmospheric pressure since it's at the top of the water surface. So P1 and P2, those pressure head terms cancel out. And then the velocity at both location 1 and 2 is 0. Now there may be like a wind blowing on the surface, and so there may be ripples, or you know, if the water level is falling a little bit, it may have some downward velocity. But the thing is the velocity is going to be so small that if you put in some number like 1 centimeter per second into the velocity head term, you know, even if you did put in the actual velocity, that velocity head term is going to be negligible. So we might as well just neglect it entirely. So what we have is substituting in the elevations and the losses, the given losses of 5.4 meters, we get that the turbine head is 127.1 meters. So, I mean, if you think about it, the elevation difference in hydropower is what's giving you the energy. And so what you want to do when you look for a site to generate electricity is you want to have the biggest elevation difference possible, because it's that difference in potential energy that's going to be converted into electrical energy. So here there's a pretty extraordinary elevation difference, 127 meters of elevation difference after you account for the losses. The losses of 5.4 meters. And so that's another thing that you want to try and minimize. And the way to minimize those losses is to have a pipe that has very little friction, or a large diameter penstock so that the velocity is low, because normally these losses are dependent on the velocity of the water flowing through the pipe. So we substituted into the power equation here. All right. If we have a cross-sectional area that's determined by the diameter of the pipe and the velocity through the penstock that's given, then each of you, as I was circulating around, I noticed calculated the flow rate, 4.24 cubic meters per second. Good. So you substitute that into the power equation. Your Q, the unit weight of the fluid, and the turbine head is what gives you the amount of power that can be removed from the system, 5.29 megawatts, because it's 5.29 times 10 to the 6th, so that's a megawatt. But that's assuming perfect conversion of the potential energy into electricity, and that's never the case. It maybe would be more realistic if we're considering the losses in the turbine and the losses in the generator, to assume something like maybe 70%, and so 0.7 times that would give us 3.70 times 10 to the 6th watts. If we go back to this slide, it said if you have a turbine, you multiply by the efficiency factor, and that's what each of you did. Is you realize it has to be less power if it's not as efficient. And so what are you going to do? You're going to multiply by the efficiency factor, and then that gives you less power, right? In the case of a pump, think about it the other way around. What if we were lifting water from the lower reservoir up to the higher reservoir? So let's say reverse this problem. What if you had to pump the water uphill? We could calculate using the energy equation the same way that we did before. You have to overcome the elevation difference, and then you also have to overcome the head losses. And so you can find out the H sub P by those things. The elevation difference and the losses tells you the HP, and then you'd put in the flow rate, the unit weight, and multiply it by the pump head. So then that would tell you, without any losses, how much energy is needed to lift the water uphill. But then if it's a pump and you have an efficiency factor, you're not supposed to multiply by the efficiency factor, because it actually means that you have to use even more electricity than you would if it was perfectly efficient. And so the way that you account for that is you divide by the efficiency factor. And so if we were lifting the water, maybe it would take 5 megawatts if there was no losses. But then if there are losses, it's going to take more than 5 megawatts. And so you divide by 0.7, and you'd get something like, 7 megawatts of electricity needed to lift it uphill. So just to summarize, when you have a pump problem, you'd use the energy equation to solve for H sub P, and then you'd substitute it into the power equation where instead of turbine head, it's the pump head as the final term. So any questions about this example or how we deal with efficiencies? Because on your homework, I think you have a problem where it's starting to talk about the power equation. In fact, I know you do. This is the problem on your homework that is dealing with the power equation. So let me give you some key ideas for this problem. Okay, so we have a reservoir in this problem. Here's the reservoir and a pump, and then the water is coming out of some orifice. And this is the kind of tool that sometimes people could use to clean their teeth. But to us, we don't care what it's being used for. We just see a pump and water flowing through a pipe, right? So for this one, we know the diameter of the jet that's coming out of this water pick, and we know the velocity that the water is coming out. So with those two things, of course, you can calculate the flow rate, Q, just like we did in the previous example. And here we're going to assume that the pump efficiency is 100%, because it's asking how much power is consumed by this device. How many watts does it need? So the first tip I'm going to give you is just assume 100% efficiency, because the problem statement doesn't say anything like what its losses are, what's the efficiency factor. Now, here's the energy equation. You can neglect the losses, H sub L, because the problem statement doesn't tell you anything about pipe friction or local losses. Then you can just cancel that term out completely when you're solving the energy equation. You can assume that the reservoir and the jet are at the same elevation, and so what that means is that Z1 and Z2 are going to be the same. And by the way, where do you think is the logical place to select as location 1 and location 2 in this problem? Okay, so 1 will be the water surface, and what about 2? At the jet. Why not the other way around? Why not make location 2 the reservoir and location 1 the jet? Okay, because it always has to be where the water's coming from and where it's going to, because the pump head term is on the left and the turbine head term is on the right. So here's the motor and the pump. That means that the water is going from the reservoir to the jet. So yeah, just as you guys were saying, 1 is here and 2 is at the jet. Okay, so what this bullet point is saying is Z1 and Z2 are equal. And what do we know about the pressure at 1 and 2? 0, atmospheric pressure, because a jet is having the same pressure as the air that surrounds it. The other tip that I'm going to give you is that you can assume the flow is turbulent. So assume an alpha is equal to 1. Now in previous examples, we've canceled out the velocity head terms. But on this one, you can do that for the reservoir, but not for the jet of water that's coming out of the water pick. So you should leave V2 as a term. Don't neglect that. So again, remember the two-step process. If you're wanting to find watts, the first thing you use is energy equation to find H sub, in this case, not T, but H sub P. And then in step 2, use the power equation to find the watts. Okay. So any questions about this example? Or not example, about the key ideas that I've suggested for this problem? All right. So hopefully that'll help you for that one. Yeah, here's the power equation. In this case, you'll notice that instead of H sub T, I've just substituted H sub P because they have the same units. Pump head and turbine head both have units of meters. Okay. Now finally, this one's a little tricky. Problem 723. This is on the set that's due coming up. You're given the pressure at 2 locations, and it's water. So for water, of course, you can use a unit weight of 9810 newtons per meter cubed. They tell you the pressure at A and the pressure at B. And then they're asking, is the water flowing up or down? Now here is the energy equation. What you're supposed to do is apply the energy equation, and so water flowing up or down. The way to test that is what is location 1 and what is location 2. If the conditions were hydrostatic, so if the water wasn't flowing at all, then you could just use delta P is delta H times gamma. And so you should be able to predict the pressure change if the water wasn't moving at all using the hydrostatic equation. But since it is moving, there are going to be head losses, H sub L. And so you can just assume one direction, and if your head losses are positive, then that tells you that you assumed the correct direction. And so what you do is you assume, let's say, if you want to check that the water is from A towards B, what you'd do is you'd say, let's call location A as 1, and then you call location B is 2, and so you put in all the information you know, the pressure that's given. It looks like the velocities are going to be the same because the diameter is constant in this pipe. But you'd put in the Z's, Z1 and Z2. There's no turbine. We can look at this drawing and see there's no pump and no turbine. And so you'd solve for H sub L. And if the head losses are positive, then that tells you that your assumption was correct. If they're negative, then that tells you that it's actually the other way around. So solve for the head loss. Substitute all the information you have into the energy equation, and then solve for H sub L. If you get a positive head loss, then your assumption is correct. If you get a negative head loss, then try again. Then make the other one location 1 and the other one location 2, and just double check to make sure when you put in the elevations and the pressures, see if the head loss is positive, and that tells you if the water's flowing up or down vertically. Any questions about that? Okay. That's all we've got for today. I think I'm going to wait to introduce this idea until next time. But if we just revisit these announcements, your homework is due on Tuesday, and then we'll have that bonus quiz a week from today. So I hope you have a great day, and I'll see you next time.